Hi guys, welcome to some level 3 chemistry. We are going to continue from our previous video, which was looking at the aqueous section, looking at the weak acid, weak base calculation. So hopefully you are now masters of using those two formula. You know, they will be your best friends for this topic because you're going to use them quite a lot in this remainder of the unit. Okay, but I'm not going to do that anymore. That's from our previous video. Have a look at that if you have any more questions. Now we are going to continue on. Now before I do species and solutions, which is actually quite an important section, I just want to mention this thing with Ka and pKa and Kb and pKb. Okay, so I'll just talk about pK first, and you understand Kb, pKb. Now, what is Ka again? Ka is the acid dissociation. Okay, so if you acid dissociation constant, and if you look at all the numbers, like say for example, I can't remember something on top of my head, like say 1.5 times 10 to the power negative 5. This could be like, it's normally a very, very small number, and it's very, very difficult to communicate using that particular terminology, using Ka. Like, it's the same as H3O plus concentration and pH. What's H3O plus? Say for example, if I have something with a 0.1 mole per liter H3O plus, I can promise you, if you go out on the streets and ask someone, hey, I've got this solution, I bought this particular thing, this has a concentration of 0.1 mole per liter, can you tell me the pH? And I guarantee you 95% of the population, probably even more, wouldn't have any idea what the heck you're talking about. Okay, unless you do science and chemistry at university, and even if they did it, they probably would have forgotten it because you don't really use it much. So how do we deal with that? The H3O plus concentration is how much hydronium is in the solution, but the general public doesn't understand that. This is why we use pH. What's pH again? pH is negative log H3O plus. So if you know the H3O plus concentration, you know the pH, which is 1. I mean, even my 5-year-old can understand what 1 means. 1 is really low, and the lower the number, the stronger the acid. Okay, so you probably don't want to drink that. So same thing with Ka. We'll go back to here. If we go back to the Ka and pKa, Ka is a constant. Okay, it's normally a very small number. We don't like communicating with small numbers. If I write 1.5 times 10 to the power negative 5 on a piece of paper, and or on the back of a product that's slightly like weakly acidic, hardly anyone's gonna understand that. You know, considering how poor we are. I keep flaming the mathematics levels at the numeracy levels in New Zealand because it's just so poor. If I put 1.5 times 10 to the power negative 5, half the nation probably don't even know what I'm talking about. Okay, so so we need to, as scientists, we need to be able to communicate the idea to the general public. So this is where pKa comes in. pKa, just like pH, what does that P stand for? P stands for negative log. So you just negative log Ka. Okay, so if you grab a calculator and you go negative log 1.5 times 10 to the power negative 5, I'll do this on my calculator, excuse me, 1.5, negative log 1.5 e negative 5, I got 4.82. Okay, I mean, this is such an easier number to talk about, to communicate. 4.82. Okay, so it's not the same as the scale on the pH of 14, like compared to the pH and pOH, but this is a much number to communicate with. Okay, so if I tell you, hey, I got this acid has a pKa of 4.82, so straight away you're like, pKa, okay, so it's a weak acid, it's not a strong acid. So 4.82, how does that look? Just remember this, the higher the Ka, the more acid will dissociate, and the more acid will dissociate, the higher the concentration of H3O plus, therefore the stronger the acid. Okay, Now, so mathematically, the lower, oops, I'm just writing the opposite. The higher the Ka, and if you negative log that, the lower the pKa. Okay, and then just go back and talk about all this stuff again, but then the stronger the acid, the stronger the acid. So it's just, you can kind of interpret it as the pH. You know, one is stronger than two is stronger than three. For example, let's say, for example, if I have something with a pKa of 0.8 versus something with a pKa of 0.8, that's really, really strong, versus something like a 4.8. 0.8 is a much stronger acid in comparison because the pKa value is lower. pKa value is lower, that means that this is a stronger acid, because the lower the pKa, the higher the Ka, the higher the Ka, the more they dissociate, the more hydronium ions it will produce, and therefore the stronger the acid they are. Okay, so that's just really, really straightforward. And how do you calculate, like, say, for example, pH equals negative log H3O plus, and how do we calculate H3O plus, which is 10 to the power negative pH? This is exactly the same as Ka. pKa equals negative log 10 Ka. Oops, this Ka is not a concentration. pKa equals negative log Ka, and then Ka equals 10 to the power of negative pKa. It is exactly the same as your acid and base calculation. So just, you know, if you know one, you know the other. This particular method you actually might need to be able to use, because sometimes they give you the pKa, so you need to convert the pKa to Ka. Let's say if you have a weak acid, you're like, all right, I need to use, let's say, for example, this is a weak acid calculation, and I gave you H3, and you know the equation, H3O plus equals the concentration of Ka times the concentration acid. And what if I go, all right, pKa equals 4.2, for example, and you're like, oh my god, I got pK, the equation needs Ka, what am I supposed to do? Well, first of all, 10 to the power negative 4.2, that will give you the Ka, and then just substitute, just one extra step. Okay, so that's not the emphasis of this topic, of this section, but it's just you just need to understand that a lot of the terminologies that scientists use are just for the sake of general public. Like, you know, no one understands what moles per liter are, you know, if you go to the supermarkets. But then if you show them pH of 2, they're like, oh, that's pretty acidic, don't want to drink it. But if you put 0.2 moles per liter, like, what the heck, you know, 0.2, that doesn't sound too bad, you know. So it's just more to do with the communication. All right. Now, species and solutions. Species and solutions is actually quite interesting. I'll just do some of the really easy stuff, like, say, for example, HCl. I'm going to do HCl. HCl is a strong acid. So what does that do? That will completely dissociate into that. So what does we normally don't include water, okay? So what does species in solutions mean? Species in solution, like, say, for example, if I have a strong acid of HCl, what the question is essentially asking you is that what are the things that are present in that particular solution, and can you rank them in terms of their concentration? Okay, so for example, if I put hydrochloric acid in water, all of this will dissociate because this is a strong acid, so it completely dissociate. So the water concentration is so big, so we don't even look at it because that's the biggest guy out there, so we just completely ignore it. So what is left in the solution? You have lots of H3O plus and you have lots of Cl minus. Now, something that you do need to get used to, and you need to remember this, I'm going to put this in the top right hand side corner. In every single species in solution comparison, you will always have hydronium ion and you will always have hydroxide ion, even though they are not present in your solution. You look at this and go, where the heck is my OH minus? Are you trolling me? Well, you need to understand that your water is actually going to dissociate with each other, and they will turn into H3O plus and OH minus. So you always have a small amount of each in every single solution that has a bit of water in it. Okay, so this is your species in solution comparison of your hydronium ion. Well, in this case, when I dissolve HCl, which is a strong acid, what are the species? You know, we're not doing biology, but this is how we call it. What are the species? What are the chemicals that is in the solution? Well, if it completely dissociate, we have lots of this. We have lots of the hydronium ion, we have lots of the chloride, and we have like a tiny amount of hydroxide ion. So this is why this is a strong acid, because you have lots and lots of the hydronium ion, and that's why the pH is really low, and that's why this particular solution is an excellent conductor of electricity, because you have lots of ions. Okay, let's do a strong base. A strong base is going to look like this. This is completely going to dissociate into that and into that. So this is gone, completely dissociated. So you have tons of this, you have tons of this, and then you have like a tiny amount of the hydronium ion. Okay, so just always remember you always have both of these. And you may go, why are they equal? Because you make equal molars of the Na plus and OH minus. And same reason as before, this completely dissociate. The OH minus concentration is very high. This is very high. And what that means is that it has a very high concentration. It's a very strong base. And then completely dissociate as well. You dissociate completely as at the beginning. You have lots of that. OH minus, therefore the pH is really high, and you have a high, strong base. Okay, also a very good conductor. Now, let's look at something from last year. If I look at CH3COOH plus dissociating water. Now this is a partial dissociation. Now this is when it gets a little bit trickier. So remember, I always use this example about if you have 100 of these at the beginning, at the end you probably dissociated one of them, and then you don't have 100 anymore, you have like 99 left. Okay, so the bulk of the solution is going to be your CH3COOH. That's the most abundant, ignore water, this is the most abundant species, because this is the partial dissociation. So you're only going to dissociate like a tiny percentage of the CH3COOH, and therefore at the end of the dissociation, the most abundant thing is still going to be that. Okay, so that's going to be the most abundant. Now then you're going to make equal amount of these. And then you always have a tiny percentage of the other thing, which is a hydroxide in this case. Okay, now this is a poor conductor of electricity. Why? Because you have a very small concentration of the free moving ions, so it's a horrible conductor. And in relative, this concentration, the hydroxide ion concentration, is very low, so that means the pH is going to be a little bit higher, and then you have a weaker acid. Okay, so hopefully that makes sense. Just combining some year 12 simple stuff with some year 13, just a new year 13 concept. It's not even that new. You would have known this from last year. It's just two things combining two things together. All right, let's do a weak base before we do some salts. The salts are the hardest one. So this is ammonia, dissociate into that. So same reasoning as what we got before. You have most of the solution being the NH3, because only a tiny percentage of that has dissociated due to the equilibrium. So you will have bulk of it being the ammonia, and then a small amount of NH4 plus, and then a small amount of OH minus, then a tiny amount of the H3O plus. Okay, so same reason, this is most abundant, very high concentration, because you have very partial dissociation. This is very low, therefore poor conductor, and then poor conductor of electricity, and because that's very low, that means you have a lower pH. Okay, then your strong base. All right, let's do the salt solution. Now the salt solution are the ones that people struggle the most. For example, let's start with some neutral salts. Sodium chloride. If I put sodium chloride in water, that's going to split into Na plus and Cl minus. Just break them into ions. Okay, that's not hard. Is this going to dissociate more? No, they don't do anything anymore. So you're going to have equal concentration of Na plus and equal concentration of Cl minus, and which is going to be bigger than your OH minus, which is going to be the same as H3O plus. And you may go, where the heck did these two come from? Well, remember, this NaCl, this is neutral. This is neutral salt dissolved in water. What is water made of? Water is made of H3O plus and OH minus, which is in a neutral solution, equal concentration. That you learned in year 11. Okay, so is this a good conductor? Yes, great conductor. And what about the pH? pH equals 7 because it's neutral. Okay, so this is just a neutral salt, just to put it in there, just to make sure you got that. Now let's put something that's a little bit harder. Now you probably spit through the other lots because they're not really that interesting, and most of it is from year 11, year 12. A lot of it is from year 12, so let's look at this one. This one's a lot more interesting. Okay, so I'll definitely take my time with this guy a little bit. So if I have CH3CO and Na, what are the species in this particular solution if I dissolved it in water? So this is 2 steps. Whenever you have something like this, this is 2 steps. First, dissolve it in water. That means you will split it into the corresponding ions. Okay, now we're not done yet. This is step number 1. Now we're gonna get here, then you're gonna like, wait a minute, this looks rather familiar, CH3COO minus. Then you should be like, hold on a sec, so if I put this CH3COO minus in water, oops, made a very common mistake. One of the H's is actually going to hop over to make the conjugate acid of CH3COH, you know, the conjugate acid of CH3CO minus, and then you make OH minus. Okay, so again, if I had, now I'm just going to use this numeric number, like say if I had 100 of these at the beginning, this will completely dissociate. I'll make 100 of these, I'll make 100 of these. And then out of this 100, probably one of them will dissociate to that, So I'll probably have 99. So I have 19, well, this is still 100 at the first step, so I still have 100. But then at the end, I'll probably only have like 99, 98, 97, like say, for example. Don't use this new numbers in your explanation. I'm just doing these for you to understand. So can you see the most abundant thing is this guy? The Na plus concentration is the greatest, because once your first step, dissociation has occurred, the Na plus just sit there. It doesn't do anything anymore. And then the CH3COO minus is going to partially dissociate. So you're going to lose a couple of these guys, and then they will turn into CH3COOH and OH minus. Oops, no, not plus. These two concentrations are going to be the same. And why is that? Because it's a 1-to-1 mole ratio. And don't forget, you always have your H3O plus. So this is much harder, as you can see. Now, we do accept, if you're someone saying, well, 199, those two are really similar. If you did Na plus equal CH3CO minus, we accept that as well. Okay, because that's technically correct. I mean, it's so weak dissociation, you're only losing a small percentage, you can just assume them to be the same. Okay, so that's that one. Hopefully that makes sense. So this is what we call, so alright, so we want you to let's summarize this. So from what we got, we know we have high concentration of this and this, so which are free moving ions. What does that mean? That means we have great conductor of electricity. Now the pH is, can you see we have higher concentration of OH minus, higher OH minus compared to H3O plus, that means the solution is basic or alkaline. So this is what we call an alkaline salt. And you may go, how am I supposed to know this? Well, we only really give you two examples. One is CH3COO something, and the other one is this guy. The other guy is this. This is the other example, NH4Cl. The same thing, two steps. Step one, dissolve it. Always separate it into the ions, NH4 plus and Cl minus. And then you're gonna be like, hey, hold on a sec, I've seen this guy a million times. This is going to partially dissociate into the conjugate base. And then you'll be like, oh my god, I have tons of the Cl minus. This have the highest concentration. I have roughly the same concentration as this. So the concentration ranking, I have lots of Cl minus. I have more NH4 plus. I mean more Cl minus than NH4 plus. If you went with equal, we accept that as well. Then we have some NH3, we have some H3O plus, then we have very little OH minus. Okay, so again, two things. This is a great conductor, and this particular section here means this is acidic. So this is a weak acidic salt. Okay, very common type of question where you just compare a the difference in the concentration of the species, and yeah, and just rank them, and you can write the equations, write the equilibrium to show your understanding, and then that's normally like a merit-ish, sometimes can even push up to like a low excellence sort of question. Okay, so hopefully this kind of makes sense. We'll follow up with some questions probably tomorrow, and we'll go on from there. Okay, so hopefully this was helpful, and take care, and I'll see you guys next time. Bye bye.